Hey, what's up, guys? This is Chung here again. This time number 1879, right? Minimum XOR sum of two arrays. So this one you're given like two integer arrays, right? Nums1, nums2 of the same length, and the XOR sum of the two integers is for each corresponding index. We do XOR for those two numbers, and then we summarize everything together, right? And you need to rearrange the elements of nums2 such that the resulting of XOR sum is minimized, right? And you just need to return the minimum XOR sum after the arrangement, right? Okay, so pretty straightforward, and the constraint is like this. So n to the power, n is only 14 length. So every time when you guys see this kind of like smaller length here, you pretty much know already we can try like using the bit mask, which means we need to have like bit mask to represent each number, right? With some state. And even if this happens, usually we can also use some DP plus bit mask, bit manipulation technique to solve this problem. So let's take a look, right? I mean, since we can rearrange nums2, it means that given for each given nums1 here, it can do XOR with any number in nums2, right? Since we can arrange the nums2 and in any way we want. And obviously there's no greedy approach here because XOR is pretty deterministic, right? It's quite undetermined when it comes to XOR because there's no such greedy way such that we find like two numbers with the biggest number and we do XOR. So because the result could be anything. That's why since there's no greedy approach, we have to try all the possible scenarios, right? And so the one fact is that since we want to find the smallest XOR sum, if we have like some arrangement, right? If we do XOR for these two arranged numbers here, if this one is smallest, any subset of these two numbers, basically, if this thing is smallest, this one, if we do XOR with this part, it also be smallest. I mean, the smallest in the sense that if there are like three numbers, if we pick three numbers, if we pick three pairs out of the six pairs, and if we want to do XOR sum, and then that three pairs will also be the smallest number. I think there's a proof for that, but I'm not going to into detail for that. So which means that now we can break these problems into a smaller size problem, right? Since we're getting the biggest one, the smallest XOR for the entire pairs, right? And so the sub problem is that any sub pair is also smaller value. It's also smallest. It's also smallest XOR sum given that size. That's why we can have like a DP state here. So basically, we can use a DP state. So the first one is I here. The second one is a mask, right? So what does this one mean? It means that I means that we are trying to basically this I means that we have already matched I numbers from 0 to I, and now the mask is that the mask basically it was just like a 1 0 1 0 1 1 0, right? So 0 means that number from that's the mask for nums2. 0 means that number in nums2 has not been paired or has not been matched before. 1 means the number has already been paired. So which means that, given the I and the mask here, so this one means that 0 to I, so the numbers in num1, right? The numbers in num1 from 0 to I has already been matched. Given this two state, this one means that the minimum sum, right? Given this state, which means that we still have some numbers from nums1 that we need to match from I to n, right? And then the second one is that and we have this kind of numbers from nums2 that we haven't matched. Given this two state, we can get the minimum value, right? The minimum like sum for the remaining numbers, and among all these kind of possibilities, we need to get the minimum, and that's the definition of this DP, right? And actually, this one is a pretty classic DP definition. We have a lot of DP problems has a similar like state definition, where the first one is a current nums1 that we're trying to match, right? And the second one is the mask, that's the candidates that we can use. So basically, to match the current ice numbers, we need to try all the possible numbers that haven't been matched, right? And once we do that, right, we can update the mask accordingly, and then we can move the I forward. And we just need to get the minimum among all these kind of scenarios, right? And with the DP, it can help us reduce the complexity, because, like I said, given this I, if the I and the mask are the same, right, and then the result should be the same, because we already know the answer, right? If we already know the answers, given this I and mask, right, we don't have to recalculate, right? We can just simply return it. Okay, cool. So, and the implementation actually is pretty short, We have defined DP, right? There's I and the mask. And then we have LRU, right, of cache, none. So if the I is equal to n, right, we simply return 0. It means that we have matched all the numbers. We can stop here, and then nums1. Otherwise, right, we try all the possible numbers from numbers 2 that has not been matched before, right? So for j in range of n, we just need to check if this bit has the value 0. So we can do a mask to this kind of bits left shift by j, and then if this one is 0, it means that okay, we can pick this one, right? And if we pick this one, it means that we're going to use this number to match the current i's number, right? It's going to be the nums I XOR nums j, right? So I think we need to have like parentheses. And then the remaining part, we can handle it to the next state, which is the I plus 1. And then the mask will be this XOR. We're going to mark this bit to become 1. Right. Okay. So return the answer. So that's it, I guess, right? DP at 0, 0, right? All right. If I submit, yeah, there we go, right? So nothing too fancy. And so the time complexity here, we have so the mask, right? Obviously, this one is 2 to the power of n. And then we have another like I here. I would say this one is like n here maybe, and then we have another n here, like, yeah, but this one is like, I think 2 to the power of n is much greater than the n squared here, right? So it's more like O of 2 to the power of n. Or you can add this one, I think. It doesn't really matter. And yeah, so that's it, right? I mean, a very classic DP plus bit mask problem, right? I mean, this is like a pattern already, right? Basically, you use two state here. You know, the first one is the one, it's a number that we're trying to, it's an item that we're trying to process. And the second one, it's the other side, like the what are the candidates that we can apply to the current number. And once we apply that one, you know, we update this mask, we pass it into the next state, and then among all those kind of scenarios, we need to get the minimum, right? Since we can break this problem into a smaller size problem, that's how we can use DP, right? Okay, cool. I think that's it. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.